Okay. Then let's move on to the main part of our agenda. Let us know if anyone's having trouble accessing the live notes or any of the material. Feel free to use the chat as well. We'll be watching that. So our first talk is going to be from Xiaocong. Will you be able to share your slides?
Yeah, give me a few seconds.
Yes, I see them well.
Okay.
And you should have 25 minutes, I believe.
Okay, thank you. So I'm going to give a status report on the ACTS project. So most of the slides I said are taken from my CGD talk. So as usual, I will start with the tracking challenge, since this is the motivation for this new tracking software. So the two concerns are the much increased CPU consumption and the tracking time with the much increased combinatorics at the Future Hadron Colliders, such as the HOHC with a pay up to 200. So we need to have a very performant tracking software that is accurate, efficient, and fast enough to not compromise the physics performance. So how could we achieve this? By using fast tracking techniques, exploiting the concurrency and acceleration with the hardware architecture. And okay, so a reminder of the goals of ACTS. So the first and also the most important is to prepare an experiment-independent tracking toolkit for future detectors, targeting at Atlas at LGC Raspberry 4. So the software is based on the Atlas tracking experiences, but we try to improve the performance, such as the straight safety and the maintenance. Also, it tries to make an open source R&D platform. So there are going to be 2 talks on this for the tracking techniques and hardware architecture. So it has been 5 years since the first commit for this repository. And in particular, there's very impressive progress since the last ACTS workshop. And the good news is that we have migrated from the GitLab to GitHub last month, allowing external contributions. And so for those of you who are not so familiar with this, this is just a few points about the design of ACTS. So it's written with the modern C++ 17 and has a highly template design, which can avoid the virtual lookup and also to allow the maximum customizability in terms of the detector and the magnetic field. And the particular care is given to the thread safety, such as the strict const correctness and use of steadiness tools to facilitate the concurrency. Also, it's very concerned about the memory allocation and access. For example, we try to use the fixed size EDM based on the eigen, which has much better performance compared to the dynamic size EDM. And the concept of context is used for the condition const, such as the geometry, the calibration, and the magnetic field, to support the concurrent event execution with different condition const. And there are modular and rigorous unit tests everywhere in this repository to guarantee the quality of the code. And also the algorithms are designed to be highly configurable for ease of use. And there's minimal dependencies for the integration purpose. And the last point, believe it or not, is well documented. Okay, so this slide here is trying to show the different components of this ACTS repository. So we have the ACTS core, which includes a few tools, as you can see here, and some of them are new features, such as the track finder, the vertexing, and the visualization. So as you can see here, we have a directory for the examples, which is actually the ACTS framework integrated into the ACTS core, for which can be used to run the event processing and concurrency test. And also we have a FATRAS directory, which is the ACTS FATRAS imported for the fast simulation engine. And so tomorrow will be a few tutorials on different components of this. So for the rest of the slides, I'll go through the different components. As usual, I will start with the geometry. So the main message here is that the ACTS tracking geometry is a simplified geometry from the full simulation geometry for the CPU and the navigation considerations. And the collections are built through the ACTS detector elements, element base, which can be converted from other detector representation for some plugins such as DDFLHF plugin. And currently, the supported detector geometry includes the silicon calorimeter and the spectrometer. And the very important components of the tracking geometry is the ACTS surface, which has most of the concepts taken from the Atlas software. So here, this is a picture for the different surface types in the Atlas software. So we have the cylinder surface, the disk surface, the plane surface, and the line surface. So all of these are available in ACTS. And so here, this is the ACTS surface bounds, which are very important for the navigation. Here are just a few examples for example, the cylinder bound, the disk surface bound. And in particular, we have the cone surface bounds, which can be very useful for some detectors, such as the Bell2 silicon detector. And the new features for the surface happened in the last few months is that we have the polyhedron representation for each surface type, which can be very important for the fast navigation. And to consider the material effects in the tracking, we have to store the material in a way. And in ACTS, we have the material mapping tools for this purpose, which can be used to map the Gentile recorded flow material onto either the described surfaces or the volume grids, depending on the detector type. And these two plots here are to validate the material mapping tools for the silicon detector and the calorimeter. And the propagator, which used to integrate the particle transport and the geometry navigation, had a highly template design, as you can see here. So it's templated on the stepper and the navigator, which used to establish the propagation scenario. And for specific propagation call, it takes a start parameter and an optional destination surface, and also the propagation options, which is templated on a few actors and voters, which can allow the custom execution and abortion at each propagation step. For the actors, it can be something like the material interactor or the common actor. And for the aborter, it can be the surface reached if there's a destination surface. And the propagation will give the results based on the actors. And the propagation step can be determined by the stepper according to the accuracy or the navigator to reach the geometry object, or the aborter to reach the target. And for the specific stepper, as you can see here, we have different steppers. The primary stepper is the eigen stepper, which is taken from the Atlas Rojikota stepper rewritten with eigen. And we also have the extension for transport in the dense volumes, such as the calorimeter. And some new features happened in the past year is that we have the timing information included in the integration, which can allow for the time measurement and with low additional overhead. And there's the recent work try to support the complete free parameter representation without binding to the surface, which can be very useful for the tracking for the gas detector, such as the TPC or the dribbled chamber, as you can see on Wednesday's discussion on this. And for the track parameter and the measurement EDM, so we have both the coefficients and the covariance based on the eigen, and we have 6 parameters for the track parameter. So including the local coordinates in either the local surface frame or the curvilinear frame, and also the momentum, the charge, and the time information. For the local coordinates, one thing to mention is that the meaning of those 2 parameters can be different depending on the surface type. For example, this here we have the parity track parameter with respect to the parity surface. So the local 0 means D0 and the local 1 means D0. And the track parameter has the multi-component representation. And for the measurement, it contains a source link to the original detector element, which can be a cluster or drift circle, and to be used as a container for different dimension measurement. STD variant is useful as a wrapper for this. And the track state EDM is, as you can see here, is designed based on the concept of the common feature, which includes the parameter and the measurement part. So as you can see here, we have the predict, filter, and the smoother track parameter, and also the transport Jacobi, which is necessary for the backward smoothing. And for the measurements, we have the uncalibrated and calibrated measurement, as I said before, which can be converted via the calibrator during the fitting. And for the track EDM, which is basically a container for the track states on the trajectories. So this is eigen-based, eigenmatrix-based, and it provides the separate storage for the parameter coefficients and covariance, both the track parameter and the measurements. And an index data class is used to keep track of the storage index. And this is very useful to allow the branching of the tracks through the parent relationship. And also it can avoid the storage duplication for shared measurements and parameter. And okay, so the track fitting, as I said, the common filter is used as an actor in the propagator. So the ACTS common filter supports the whole search and outlier rejection during the fitting. And there are two approaches for the smoothing. We can use either the smoothing formalism based on the Jacobi from the forward filtering, or run another backward common filtering for the smoothing. And also we have the line Gaussian extension for the common filter, which has been there for a long time, but that's not merged. Okay, and so this is the parity track parameter resolution. So it's not perfect Gaussian because we have very little material for the track ML detector, but roughly it's okay. And for the common filter performance, we have looked at the fitting efficiency, which is defined as the number of tracks that has fit successfully and over the number of truth tracks. So as you can see here, it's effectively 100 fitting efficiency. And this is validated with particle down to 100 MeV. And for the timing, so for a single track, the time is around 0.2 milliseconds. And for the track finding, so currently we have our computatorial seed finder, which is well tested for the track seeding. And the seed finder is designed to be very friendly to the parallelism, as you can see later from Georgiana's talk. And we also have the combinatorial common filter for the track following. So the difference between the CKF and KF is just that the track fitting and the finding is merged here. So if there are multiple compatible measurements found on this surface, will allow the branching of the tracks. And the measurement selection is based on the common filter chi-square. And we also can allow the stopping of bad quality branch for the CKF. And in terms of performance, so on all the hits with the truth particles, from the truth particles with momentum up to above 100 MeV are considered. So for the efficiency, we have 99% efficiency in the viral region of the detector. And for the fake rate, is below 10⁻⁴. And for the duplication rate, is 5%, but of course, this can be suppressed by using tighter category criteria for the cluster selection. Okay, so for the primary vertex finding and fitting, we have quite a few vertex tools transcribed from the ATLAS software. And their performance are well validated against the ATLAS software. But of course, it could be very interesting to have the new techniques. So basically, there are two approaches for the vertexing. So one is the fitting after finding with the iterative vertex finder, and another is finding through the fitting with the adaptive multi-vertex finder. For both of these vertex finder, we need to have a few tools, such as the seed finder, the vertex filter, and the other tools such as the track selection, track linearizer, the impact point estimator, and the deterministic leading tool. So for the iterative vertex finder, the idea is that we start from our vertex from the seed finder, and we select the compatible tracks, and then these tracks are used to perform the vertex fitting with the vertex fitter. And after that, the tracks are removed from the track pool, and we will repeat this procedure with the remaining tracks until no track is found. So one feature of this is that when each single track is always associated to at most one vertices. And for here, the seed finder is based on the z-scan seed finder, which is based on the zero values distribution. And for compared to this, we have adaptive multi-vertex finder. So the procedure is very similar, but the difference is that the track selection is from the global track pool. And if there are shared tracks found, the tracks will be fit simultaneously. So with the deterministic or leading tool, the tracks can have weights to multiple vertices instead of just one vertices with the IVF. And the seed finder here, we have since two seed finders here, which are both based on the Gaussian track density, which try to model each track with their distribution along the z-axis based on the D0 and Z0. Okay. So in terms of vertexing performance, the vertex precision resolution agrees well with Atlas results. But for the timing, we have seen very significant speed up with the Atlas software. So this is the case for the Gaussian grid track density seed finder, and also the MVF. Okay. So this is the application to the detector. Just to mention that we have a lot of new detectors implemented with ACTS in the past year. So as you can see from the lot of talks later in this session. And also the R&D. So the R&D for both the new tracking techniques and also the new hardware architecture, there are going to be 2 talks for this. So I'm not going to into detail for this. Okay, so this is a summary of my talk. ACTS has grown quite a lot as a tracking toolkit over the past year. We have seen a lot of consolidation of the tracking infrastructure, such as the geometry, the propagator, and the EDM. And also we have new tracking features implemented, such as the feature, the track finder, the vertex tools. Also, ACTS is a very active R&D platform for exploiting the new tracking techniques and hardware architecture. In particular, there's growing interest in experiments for both application and contribution, such as the FADA, CPC, S-Finis, and the BEL2. So one thing to mention that the ACTS members has grown from around 27 to 50, so maybe more in the past 1 year. And in terms of some future perspective, so in the short term, the focus will be facilitating the detector application and the software integration to prepare the Atlas for the LTC Run 3. And in the long term, this is to provide a full tracking solution for the Atlas at LTC Run 4. And there will be discussion sessions, as Andy said, on both Wednesday and Thursday for some mid and long-term and core and R&D plan. So welcome to these sessions. Okay, thank you. And this is all my talk.
Great, thank you very much. Let's start with questions in the live notes, but if anyone has a question they want to ask, just raise your hand and I'll call on you as well. So Andy, do you want to go ahead?
Sure. I have two things to add. First of all, for this sounds rather complicated way of extending the propagator with actors, I have uploaded a small tutorial for tomorrow, which adds a small actor to the propagator. So if you want to change the functionality of the propagator, you can learn that tomorrow. And the second item I throw in, which I really have not made my mind around at all yet, is it always resonances in my head that Sergey has tuned at the order of 10,000 parameters for being as fast as possible in the TrackML challenge. And that included for the CKF, for instance, regionally different windows, depending where you are and etc. Things you could even probably easily learn nowadays with some modules, but we have not yet really discussed a way how you put that back into the code. Rather than a set of parameters which for the moment are all hand tuned. So this is something which whenever I see a CKF, I think I remind myself of Sergey. So this is something I would like to discuss at one of the 2 days.
I guess those were more comments than questions to have, but that's fine. Okay. So then I had a question. This was more to the talk. When you were discussing the track EDM, you were actually saying that the Kalman filter had inspired a lot of the design. I was wondering how much, if this causes any issues, and how well it will generalize to other algorithms.
I have no idea. I think this is the other tracking algorithm does not have to use this track state. For example, I think it doesn't have to have those parameter.
Yeah, when probably what I would add to this header is in the review of the tracking code. I think of at least of Atlas, but I think that's in general the history is at the beginning when we started the LHC runs, we really thought about the event data model that is used in the reconstruction being available all the way down to analysis, and analysis on ESD at that time was something that's practically impossible from the memory. And both Atlas CMS go to a nano format and analysis, which gives a way more flexibility in the EDM, in the transient EDM, to my mind, to be optimized for the algorithm. So you can have a track state-based EDM for a Kalman filter, and you can have an optimal one for a global chi-square filter if you want, or a multi-component one. And as long as it stays in its ecosystem, it can be quite optimized. It's only when then you talk to the vertexing, it should have a few that is unique, and that's sort of what we try to fulfill so far.
My question was actually a bit different. I wasn't thinking about, how you want to have it at various stages in the reconstruction. I was thinking in terms of ACTS being a toolkit for many different detectors and many different algorithms, if we're going to be limited by having a structure that's strongly Kalman filter inspired. This was more the motivation.
No, that's sorry. I did try to make this clear, but I was super failed then. What I was saying is these data structures we're using are really simple lists and collections, meaning you can nail them for the Kalman filter, make one, and then make for another one using the same classes, parameter classes, Jacobian classes, etc., and reorder them appropriately for your other algorithm.
This kind of doesn't hold for the dedicated data structures that we introduced, sort of designed for specifically for the CKF though, where this class here, this track state class, isn't actually explicitly used anymore, and the Kalman filter in the majority of the code also doesn't use this data structure anymore, but uses this multi-trajectory collection, which is has this structure basically hard-coded in. So
what I meant, you tailor it for your algorithm. but you use
Right,
the
but
same.
that's
Yeah.
not flexible. You can't configure it. You have to rewrite it, basically.
Yeah. So this is just the concepts for
That's
the
true, yeah.
yeah.
Okay, other questions? I don't see any more in the live notes. Anyone can speak up as well if you don't want to raise your hand. Okay, if not, then thanks, Xiaocong. Let's move on.